Hello everyone, welcome back to ptet.chemistry channel. My name is Dr. Ont. In this tutorial video, we'll go through this IGCSE chemistry. This is an alternative to practical, paper 6 for the October-November 2022. So this is paper 6, variant 3, 1 hour, alternative to practical paper. In this first question, we have this hydrogen chloride, which is a colorless gas. What is very important is this information here, soluble in water and then denser than air. If it is soluble in water, then collection over water is not a very good method. If it is denser than air, if you're going to do a collection in a gas jar, the gas jar has to be similar to this because the gas will be coming in and the gas will be denser than air. So there will be a better method than the other way around, because if it is the other way around, if you have a gas jar that looks like this and then your gas particles which are denser than air is gonna escape from the very bottom, so that will not be a very good method for collecting the gas. Then collection over water is not very suitable here because the gas is soluble in water. So collection over water, that is basically you have a tubing that goes into the inverted measuring cylinder in water. So this hydrogen chloride can be made by reacting sodium chloride and concentrated sulfuric acid. That is the instruction given, just by reacting sodium chloride and sulfuric acid. So this is the apparatus that the teacher used in order to make this HCl gas. So hydrogen chloride is pronounced as such. That is because you have hydrogen and a chlorine. Hydrogen with 1 electron in the outer shell, chlorine with 7 electrons in the outer shell. Really want to just share 1 electron to complete the outer shell. So you're left with 6 more electrons on the chlorine. This is a single covalent bond. This is HCl. This is called hydrogen chloride. Hydrogen chloride is a gas that's very soluble in water. Then you can get HCl, which is a strong acid, and they will dissociate or they will ionize completely in the presence of water to give you the solution called hydrochloric acid. So there is a difference between acid as well as the pure substance called hydrogen chloride there. Hydrogen chloride is pure, hydrochloric acid is what you call a mixture. It has been dissolved in water, whereas hydrogen chloride is a pure substance there. Anyway, in the actual alternative to practical, we are more concerned about the questions as well as the practical techniques. So let's just get started. Name the items of apparatus. So apparatus A is nice and easy. Apparatus A is just this container, and this is what you call the conical flask. And what is apparatus B? Apparatus B is just this test tube that is held by the string here, a cotton string here, which you can just pull and then this will tip over and they will start reacting without any loss of gas because you already sealed up the tube beforehand. The flask beforehand. So this is just your classic test tube. A boiling tube might be a bit too big to fit into a conical flask, but it really depends on how big your conical flask was to begin with. All right. The next bit, describe how this reaction is started. As mentioned before, the idea is that when the sodium chloride comes into contact with the sulfuric acid, they're going to start releasing or producing this hydrogen chloride gas. You don't want the gas to escape. You want it to be collected directly. And therefore, we don't want them to mix before I actually seal it up with this stopper, which is usually a rubber stopper, or you can say, it's like a rubber cork, C-O-R-K there. So describe how this reaction is started. Describe. So we can pull the string, pull the cotton string. So you could see that there was a cotton string attached to the test tube there. Attach the test tube, then the test tube will tip over. And when the test tube tip over, so the tube tips or falls over, and the solution inside would mix, and the solution inside mix with the sulfuric acid or mix with the acid, and therefore kicking start your reaction there. In part C, a student suggests the gas can be collected and its volume measured using this setup. As mentioned earlier, we were told that this gas hydrogen chloride is actually denser than air. So we said that this method is not suitable, but this method is entirely suitable there because it's denser than air. However, having said that, that is assuming you can see the gas, but we have a big problem. Our problem is explain why the volume. You can collect the gas, there's no problem. But if you can't understand the question, the volume of gas collected cannot be measured. So you want a quantity, you will use a measuring cylinder instead of a gas jar. So you will see that this one is not a gas jar because a gas jar is just for collection. Just for collection, you can use a gas jar. But then if you want to measure how much there is, you will need something like measuring cylinder. But the thing is, measuring cylinder has got lines. However, your gas is colorless. So the hydrogen chloride gas is a colorless gas. So the fact that it is a colorless gas, so you cannot see it. And if you cannot see the gas, how can you measure its volume? So therefore, we cannot see. We cannot observe how much volume, how much was being produced or how much volume it occupies. Even though it is more dense than air, yes, we can collect it. But if you think about can measure the volume, this method is not suitable at all there. So that's why this question asking why is it not suitable to measure the volume of gas there. In part D then, so how we could collect the gas to measure the volume of gas. So number one, you want to collect the gas. So do not use the one that's over water because as mentioned earlier in the question, it's soluble in water. And as also mentioned, we want the volume of gas. So what we could do is we could use something called a gas syringe. So a gas syringe will have a tubing. Well, not really a tubing, like a syringe actually. So it will have line. What is very important is it has these graduated lines. And this graduated line allows you to read the volume of the gas because they're going to push the piston. So this is what you call the piston on the syringe. It's going to push outward as the gas produced inside here, free of water. And you will need to see the color because you will just need to read until where does the piston get pushed out to. So this is what you call a gas syringe there. So we have completed the diagram. We have labeled the diagram for 1 mark. I think it's all right there. Part E, hydrogen chloride is a toxic gas. Number one, it's a toxic gas. Sulfuric acid is corrosive. As you know, concentrated acid definitely can burn your skin. So it burns the skin. Toxic gas is poisonous or is toxic to you. It can kill us. So what is the safety precaution? In terms of hydrogen chloride, they don't ask in terms of sulfuric acid. That comes after this. So let's talk about the toxicity of the gas. So the fact that it is a gas means you could breathe it in. So do experiment in a fume cupboard. So in a fume cupboard, you have got the ventilation. The ventilation will suck up the toxic fume and therefore preventing you from breathing in the toxic fumes. Now, in terms of the sulfuric acid, it is corrosive. A lot of, a very poor answer would just say use glove. So just glove on its own is not acceptable because you can use kitchen glove and they will not protect you against the corrosive nature of sulfuric acid. So you've got to use something called chemical resistant glove because in the laboratory, we're talking about this kind of chemical resistant glove, just like doctors will have done, we have used when trying to handle, like really toxic viruses, not really toxic, really dangerous viruses or to prevent infection and whatnot. That's it really for this 7 marks first question. In this second question, so we have this student who tried to investigate the rate of reaction. So this is how fast the reaction is going. Doesn't matter what this is sodium metabisulfite. The name seems a bit funny, but this is just about alternative to practical. So we are just manipulating and analyzing the data in this question. This is about the rate at different temperature. We know that as temperature increases, we know that kinetic energy, because kinetic particle theory. So this is of the particles. What happened to the particles? They gain kinetic energy. They move faster. So the speed is faster. So what we can say is they will collide more frequently. As they collide more frequently, and then this will lead to more effective collisions, and then the rate will increase as well. So 5 experiments were done at different temperature. Quite a lot of instruction here. So we first started by reading the questions because we don't just jump on. Spend a bit of time on reading. 70 cm cube K, this is potassium iodate. I believe we're given the formula, are we not? Not really, no. Okay. So we have 70 cm cube. We use a measuring cylinder. Not the most accurate thing, but it's alright to measure volume of solution in the lab. So we're going to add 5 cm cube of aqueous starch. So starch in the presence of iodine. So starch and iodine, think about your biology. Starch will go blue-black if you have iodine. So it's to detect the presence of iodine. If I2 aqueous is present, then you will go blue-black. If not, it will just remain colorless. So 5 cm cube of sodium metabisulfite was added. So you add in 5 cm cube of this other reactant. And you start the stop clock. We call it stopwatch instead of stop clock. So you can use this term interchangeably. I usually use stopwatch instead of stop clock until a sudden color change was seen. So no iodine, so it was colorless. But now this sudden color change is when the iodine get produced, and therefore it will go blue-black. So the color change will be from colorless because no iodine. You did not start from iodine, you start from iodate. And then this will go to blue-black because starch is present. In the presence of iodine, then it will go blue-black immediately. So the stop clock was stopped and the temperature was measured. So you measure the temperature using a thermometer, and then you rinse the whole thing with distilled water to repeat it. When you repeat it, so what is the same and what is different? So that is the same volume. That is the same volume of the indicator starch, so that's not your reactant. And what else do we have? We then warm up. We warm up over a Bunsen burner to about 35 degrees Celsius. So this is basically what is changing. So what is changing in an experiment? This is what you call the independent variable. Independent variable is on the x-axis, is what you change in an experiment. What are we measuring? We're measuring the time taken. We're measuring the time taken on the stopwatch or the stop clock for the color change to see. So again, for that color change, then the stop clock was stopped. So this is what we are measuring, the time taken for the color change to appear, for the color change to happen. What is the time taken? So this is what we measure. So what we measure in an experiment, that is what we call the dependent variable. Now from the time taken, we can get the rate because we know that as time increases, the rate is going to go down because the thing will be slower. That means we have a inversely proportional relationship such that we have 1 over time. Time shorter, rate will be faster. Time longer, rate will be slower. Now you repeat the whole experiment, but now you do it at 40 degrees Celsius, you do it at 45 degrees Celsius, you do it at 50 degrees Celsius. The thing is, if you read the question, this is about, because control of temperature is not precise. It's quite difficult if you're just warming it up with just a Bunsen burner. So something you could have done, in order to have better control of temperature is to use something called a thermostatic. Thermostatic means you will control it with a dial, which is actually fitted with a thermostat, and this is a thermostatic water bath. And water bath is suitable for this as your temperature, is above the melting point of ice, because these are normal temperature, and the water will remain as water, and it will not have boiled yet because it is still lesser than the boiling point of water, which is 100 degrees Celsius. So we're going to read these diagrams and interpret the data. Make sure that when you read temperature, it's to the nearest, we talk about 0.0 or 0.5 degrees Celsius. Think about the experiments you have done in the laboratory with collection of temperature. So here, this is our thermometer diagram. This is 20, this is 15. So be aware that we are reading upward here. So there's 15, 16, 17, 18, 19. So that is 19, but 19 is not really correct. It's 19.0. Now in terms of this stop clock or stopwatch diagram, so this looks like one of those analog, like really old school kind of stopwatch. These days we're pretty much using digital, but regardless, still need to know how to read these. So the inside hand is the minute. They even told you that the inside hand is minute. So the one I've highlighted in green there, that is the inside hand that is in minute. So that is 0, that one is 5, so this one is 1 minute. But they want this in second, so be very careful. Read it first. 1 minute for the short hand. The long hand is second. So let me just highlight this in pink because it might be better if it's color. Although you're not allowed to use highlighter in exam, of course, yeah. So what do we have there? We have 0 all the way to, oops, sorry, big circle, 0 all the way to 30. There's 35, 40, 45. So this is 31 seconds there. So 1 minute 31 seconds, that's going to give me 60 seconds for 1 minute, and then plus 31 seconds, that's going to give me 91 seconds altogether there. Now the next one, in terms of temperature, 30 there, 35 there, so this must be 34.0 degrees Celsius. The unit was already given in the question, that's why when we label our table, we have to know how to label them with the units in the header. Okay, so here what do we have? We have 0 minute, and we have the longhand for the second, 45, 50, 51, 52, 53, 54 seconds there. The next one, the thermometer reads somewhere in between, so you need to be careful about this. So we have 40, 45, so there's 41 and 42. This is in between 41 and 42. This is 41.5 degrees Celsius. Shorthand there is 0 second. Longhand there is for the second. Sorry, shorthand is for the minute, 0 minute. So longhand is for the second. 30, 35, 40, 41, 42, 43 seconds there. Did they ask us how many decimal places? They didn't, but this is very clearly to the nearest second, as we can't really read in between the line there for the second if you could, read the diagram correctly. For the thermometer, next one, we have 46.0, and the time there is 0 minute for the shorthand, and the longhand 35, 36 seconds there. Last but not least, we have these 52.0, as that's 50.0, 51.0, 52.0 degrees Celsius. And then this one is longhand for the 30 seconds, 31 seconds there. And that's it for that, easy 4 marks there. Now we're going to complete a suitable scale on the y-axis. So they haven't given you a scale, so you need to think about the scale. Be very careful. Draw a curve. So here they already told you that it's a curve, so do not go and draw a straight line graph there. So on the x-axis, this is temperature in degrees Celsius. This is the time to change color in second there. So temperature 19.0 and 91 second, 19 and 91. Actually, we need to figure out the scale first. That's why they give us a little bit more marks than usual. In terms of the time, the highest is 91, the lowest is 31 to 91. 31 second to 91 second. You need to have regular intervals. So let me think about this. If I started with 2, 4, 6, 8, 10, so that will be 20, 40, 60, that would be okay as well, 80 and 100. So that I can think about 31 second just now, right? 91 second for 19.0. 91 second. If this is 80, this is 90 there, because 90 is halfway in between 80 and 900. 90 and 100 in between that. So 91 is going to be in between 90 and 92. So that was, see, I forgot my temperature already. 19.0 and 91 second. 19.0 should be there because this 10 is 20, is 15, 16, 17, 18, 19. 19.0 and also 91. So that should be roughly there. Use a cross. They didn't ask you to use a cross. Avoid using a dot. Always use a cross so that it's much easier to see the point on the graph, and make sure you use a dark enough of a pencil as well. Now the next one, 34 and 54. 34 and 54. This is 30, 34 and 54. So 34, 54 is there. I mean 31, 32, 33, 34. This is 50 there. So 52, 54 there. The next one, 41.5, and also 43, 41.5 and 43. So 41.5 is there, 41.5 and 43. So should be roughly there. So that's 41, 42. So 41.5 is in between. This is 42, this is 44. So 43 is somewhere in between there. So there's just a nice cross inside the small square itself. Next one, 46.0 and 36. 46 and 36. So we can see 46 here, 46 and 36. 36 should be here. 36 is 3 small square above 30. 36 there. There's 46 and 36. Last one, 52 and 31. 52 and 31. 52 and 31. So I can roughly see my curve. Now I just need to make sure that I can probably, nope, okay, that doesn't work out quite well. So let me see if I can draw a better curve. Nope, I think the software doesn't allow me to, you know, kind of plot a very good curve. Okay, I tried to use the software to try and extrapolate a curve. That doesn't quite work as well. Okay, this is getting frustrating. Nope. Okay, I'm gonna try one last time. I'm gonna try and force it to, you know, kind of plot a curve for me. It really doesn't want to do this. Okay, I did say I was gonna try one last time. That doesn't quite work out as well. Okay, never mind. I'm gonna freehand sketch this now. All right. Let's see. So we know it's a curve. Okay, that doesn't look so good. I mean, it was quite good at the beginning. Oh gosh, okay, this is terrible. I can roughly see that it's going to go down like this. So perhaps I should try and, okay, just gonna try this now. And then just gonna continue that further. Does that work? Nope, that doesn't quite work out so well. So it's not as easy as it looks on the paper. Yeah, okay. I mean, even on the paper, it's drawing a curve takes a bit of skill, right? Gosh, okay. I'm getting very, very frustrated here. Very, very frustrated here, actually. There's a terrible, terrible curve there. Then maybe I can just, oh gosh, okay, this is really, really looking terrible here. I've spent quite a few minutes on this and I still cannot get it. Okay, so I'm gonna continue. Oh gosh, all right. Well, I mean, at the end of the day, we can just try our best to try and draw a curve. I still cannot. I really can't, okay? Let me try and draw it from this way around. That doesn't quite work out. So what happened then if you're in the real exam and you try to draw this to the best of your ability and you only have like, what, 4 minutes to do this? I mean, I'm pretty sure that I plotted my points correctly. I'm probably not going to spend so much more time on this because, you know, otherwise I won't be able to finish the whole exam, to be honest. All right. Now, deduce which experiment had the fastest. So be very careful about this word. Fastest means it will take the shortest time. The shortest time. So which experiment number was it? The one that took the shortest time will be 31 seconds, experiment number 5. And that one was the one at the highest temperature. They asked for which experiment, so that must have been the experiment number 5. The next one is using your graph. From your graph, so this means that you must show construction lines. So get your ruler and your pencil out. And this is the time. You want the time taken for it to change color at a temperature of 60.0 degrees Celsius. You did not do the experiment at 60.0, but what we want is we want to continue this curve until it reaches 60 degrees Celsius. So perhaps you can see that the curve is going to curve downwards like here. So I can project it to go somewhere like there. Could be a bit lower depending on your graph. So this is my extrapolated. Extrapolated means extended. You extended your graph to where you think it should be. So this is my 60 degrees Celsius there. And what is the reading on the y-axis there? So I will use my ruler and I will use pencil in order to show the dotted line like that. And this give or take is 20, 22, 24, 26, 28, 28.0. Oops, sorry. We did the thing to the nearest second. So I would say that's probably around 28 seconds there. and they don't have the unit, so make sure that you show the unit if they don't show you the unit. Show clearly on the grid how you get your answer. You do get 1 for the construction lines, you do get 2 to read the reading on the graph based on this 60 degrees Celsius there, and you do get the 3rd mark for the correct value and the units there. Now, experiments are often repeated. You know that about titration, we repeat it for consistency issue, and this is basically to check that they are reliable. Why is it difficult to do for these experiments? If you look back at the original experiments, your temperature was not like one of those easy numbers like 20 or 35 or 40 exactly. These are like very close to where you want it to be, but you are not going to be able to replicate your experiments to exactly have the exact same temperature as this thing where you started from things like 46.0 or 52.0 degrees Celsius. So it's to do with the control of temperature. So it's difficult to replicate to the exact same temperature, as for the above experiment. So basically it's difficult to come to the same temperature as the experiments above if you are to repeat the experiment. If you are to repeat the experiment, it's difficult to come to the exact same temperature as above. Now suggest why the aqueous potassium iodide is warm before you add it rather than after you have added, because we're trying to monitor, okay, we're trying to get the rate as temperature changes, as temperature increases, or as temperature changes in the experiment, right? So after you have added in the other substance, then temperature might have changed depending on whether the reaction is endothermic or exothermic. So we have to get the temperature of the solution before we started reacting, so that we can say, that is the temperature of the solution itself, rather than after you have reacted. So really, this is talking about the reaction. The reaction might cause further change in temperature. So we don't want that to affect our reading. So because it could be exothermic or endothermic, we really don't know, because we are not given that information. Neither are we supposed to know unless that's what we are trying to investigate. So hence we must collect the temperature. We must gather the information, the measurement thermometer, the measurement on the thermometer for the temperature before the reaction started. Hence we record the temperature of the solution before the reaction started. Of the solution before we start the reaction here. Before starting the reaction, we have to get the temperature of the solution. Next one, you use a polystyrene cup. So polystyrene is just a polymer instead of the beaker. Explain the advantage of using this warm potassium iodide to a polystyrene cup rather than leaving it in a beaker. So we know that this polystyrene cup is a good insulator. It's kind of like plastic, but it's not exactly like polyethylene plastic. It's a different kind of polymer. So for 2 marks, we got to talk about error. We got to talk about improvement of error, as with any analysis of experimental procedure. The first one, of course, is polystyrene cup, or polystyrene is a good insulator. If it is a good insulator, it will prevent major heat loss. Prevent major heat loss from the experiment or from the warm potassium iodide potassium iodate, because you don't want the potassium iodide to cool down very quickly, as you want the reaction to take place at the temperature of the solution to begin with. As for the second point, we can say that due to this, as a result, due to you minimizing heat loss, so hence more accurate data, more accurate measurement of the temperature, of the solution prior Prior basically means before reaction started. It will give you a more accurate data for the temperature. However, so why it is not a good idea to put in the aqueous potassium iodide before it is warm. So just now they say, what is the advantage? Why is it good? But then, why is it not a good idea to put it in there before it is warm? We can put it in there after we have warmed the potassium iodide and it'll be good. But then if we put it in there, that means we still have to heat. So it means that we still have to heat. We still need to directly heat up the cup in order to raise the temperature of the solution within, temperature of the potassium iodide. And you can imagine this become a problem. We can heat up the solution inside a beaker, but there's a problem. We could not directly heat up the polystyrene cup, because then therefore the cup will melt. Imagine putting the polystyrene cup onto direct flame, and that would cause an issue there because they would definitely melt the plastic cup. Yeah. So how about sketching on the grid? So you got to sketch on the same diagram when experiments are repeated at a higher concentration. So what does higher concentration mean? Concentration is in mole per dm cube. So higher mole per dm cube. So we're looking at higher mole per dm cube. Therefore, we have more reacting particles per unit volume. If we have more reacting particles per unit volume, so that means they can collide more frequently. So therefore, we talk about particle colliding more frequently. This is to do with kinetic particle theory. If you collide more frequently, your rate is going to be faster, your time taken is going to be shorter. If the time taken is going to be shorter, the rate will be faster. So we are using these same temperature changes, but we have higher concentration. So for each temperature, the time taken will be faster. So that means we are looking at, oh, my graph is not going to be pretty, but I'm just going to show the curve. Oh, there you go. It's drawing this much better curve down there. And this is to be for the part H, because this is a faster reaction. So the time taken will be shorter. At each temperature, higher concentration will be faster there. So that is part H there. So this is for part H, where at this particular temperature, the time taken is faster. At this particular temperature, the time taken is faster because this one is at a higher concentration of the potassium iodide, and that will result in more frequent collision of the reacting particles. That's it really overall for this 18 marks question. In this question number 3, we had this one solid N and also solution O. So we were told that this solid N was zinc carbonate. That means it contains Zn2 plus ions and also CO3 2 minus ions. In the new paper 4 syllabus from 2023 onwards, you have been given the alternative to practical. You have been given the test for ions results. But bear in mind that these results are not included in your other theory paper. It's still good to actually know the results by heart, as well as your experimental skills from the whole 2 or 3 years of your curriculum. So this test on solid N, we're going to add some dilute acid. Acid is going to react with the carbonate, because the test for carbonate is just by adding dilute acid, and then you will get effervescence. We're going to test for any gas produced as well. So number 1, we will get effervescence. Effervescence basically means rapid bubbling. Rapid bubbling means a lot of bubbles. This indicates gases. So that is your first observation. They're asking for observations because any gas produced, for example, you get effervescence or bubbling, indicating that there is a gas produced. What we can say is bubble the gas into lime water. When you bubble the gas into lime water, then this is the test for carbon dioxide gas. So lime water will turn milky or it will turn cloudy, whichever one you use will have been alright. And then identify the gas only after you get a positive result. The gas produced is carbon dioxide because you had just reacted. The zinc carbonate plus your dilute hydrochloric acid will give you the salt, zinc chloride, and carbon dioxide and also water. you are not asked for the chemical formula or the balance equation, I'm just going to write one for you. The salt is called zinc chloride. So this is ZnCl2 there. Because of Zn2 plus and Cl minus, 2 and 1 based on the valency, the charges of the ions. As you cross multiply the valency, you're going to get how many. This is how we have labeled to get the formula of ions ever since year 9. So we need 2 of these Cl minus there. The formula ZnCl2 will produce CO2 will produce H2O as well. Cannot write equation without balancing it. There is 2 chloride, so 2 HCl, 2 hydrogen, take away 1 oxygen, H2O, left behind CO2 as the other product there. Next we have the questions. So this mixture formed in a boiling tube, you filter that. The filtrate is the solution, is the liquid that passed through the filter paper. And the reason why we do this is probably because, some of the carbonate did not react. So that means that we only want the solution that passed through. What we have is Zn2 plus aqueous, because we had the zinc chloride. So Zn2 plus aqueous. We also have Cl minus aqueous. Aqueous means dissolved in water. They pass through. All carbonates are insoluble except when you contain sodium ion, potassium ion, or ammonium ion, part of year 9 or year 10 solubility rules. We divide these portions, we divide these solution P that contain these soluble salt into 2 test tubes. First of all, add some aqueous sodium hydroxide. This is your test for cations, metal ions here, which happen to be zinc 2 plus. So in those are our observations, again plural, because what happened when you add a few drops and then until it's in excess, as stated in the question, first a few drops until it was in excess. So initially you get a white precipitate forming. So white precipitate, that means white solid forms, but then that is when you add a little bit. And then in excess NaOH aqueous, because according to the question, we don't add NaOH, we added aqueous NaOH bracket aqueous. The precipitate will dissolve. Now that is not good enough. When we say the precipitate dissolve, the precipitate is soluble, what does it form? It gives you a colorless solution. Observation, even in a real practical, is about full observation, especially when they dissolve. What do you get in the end? Now we also added aqueous ammonia. This is also used to test for cation as well. That's why you have 2 columns. Again, the observation, you will get a white precipitate forming initially. We are not allowed to use abbreviation in your theory paper, which this one is actually like a theory paper. So again, you're not allowed to use PPT except for practical paper 3. So this is NH3 aqueous. This means aqueous ammonia. In excess of this solution, the precipitate will also dissolve, because this is to do with the zinc ions, Zn2 plus ions. So zinc hydroxide will dissolve in excess ammonia, and you will get a colorless solution also. It is the aluminium Al3 plus that give you white precipitate with ammonia aqueous, but that precipitate will be insoluble in excess ammonia. That is Al3 plus test. I'm going to test this on solution O. First of all, we do a phlegm test. Phlegm test is new in the 2023 syllabus for the Cambridge International O-Level. Although it has been the IGCSE syllabus for some time now, this gives you the lilac flame. This tells you that potassium ion is present. In the Cambridge International O-Level syllabus, there's a bunch of cations that each have their own distinctive flame color. Make sure you know those flame color as well. Now we use universal indicator. This is from the acid, bases, and salt topic of the syllabus, where you're supposed to know the changes in the color of the universal indicator. This turned purple. Purple is a much darker shade of blue. So blue on the universal indicator is around pH 9. That's for weak base. Whereas purple is around pH 13, pH 14. We are looking at a strong base. Now 1 cm of dilute nitric acid. So this is just to acidify the solution, and also to check do we have carbonate or not. No change, no effervescence. So this will tell you that there are no carbonate ions. So not carbonate ions. We added silver nitrate aqueous. So it's a solution. That one is used to test for halide, which is group 7 anions as stated in the syllabus: chloride, bromide, iodide. Silver chloride would be a white precipitate. Silver bromide would be a cream precipitate. Silver iodide would be a yellow precipitate. None of them is present because no change. Now we added in some aqueous copper 2 sulfate, and then we add in excess the third portion. This copper 2 plus is really what we test for. It contains Cu2 plus aqueous. Not too surprising, we get a blue precipitate, and this is when we add hydroxide, because this is your classic precipitation reaction. The Cu2 plus aqueous from the solution in the test tube, you must have added hydroxide because it was a base or alkali that give you the purple color with the universal indicator. Base contain OH minus, so this OH minus will react with Cu2 plus to precipitate out copper 2 hydroxide. We must balance our equation. This is 1 of the copper 2 plus and 2 of the OH minus, as you would have known from chemical formulation. This is OH minus from the hydroxide ion. 2 and 1, exchange of the valency, and then you're going to get 1 of the Cu2 plus and 2 of the OH minus, CuOH twice. The name is going to be called copper 2 hydroxide, as you will have learned in your redox topic. Use Roman numeral, especially to name transition metal compound. Deduce the pH, so this would be pH 13 or pH 14. There will be indication for a strong base, for a something that will turn purple with a universal indicator there. Identify solution O. Earlier we said it contains K plus ion. We also say contain OH minus ion. This reaction with the copper 2 plus further confirm that there is hydroxide ion. So there is potassium hydroxide, but not yet complete, because the question say solution. So this must be aqueous potassium hydroxide. Identify. You can also write KOH, aqueous. That would have been acceptable as well. That's it for that 9 marks question there. In this question number 4, so many fizzy drinks contain phosphoric acid. This includes things like Coca-Cola or Pepsi. You can check out their ingredient next time. So this acid reacts with sodium hydrogen carbonate. As we know, sodium hydrogen carbonate there, Na+. This is hydrogen ion combined with carbonate ion. H plus and CO3 2 minus give you HCO3 minus, such that the chemical formulation there is NaHCO3. Just like carbonate, they will react with acid to give you metal salt, to give you carbon dioxide gas, which is your effervescence, your rapid bubbling, as well as water. So they have this value Coke as well as Cola. They are called 2 fizzy drinks. Very, very random names, of course. These contain this phosphoric acid as the only acid. So the only thing that can react with a hydrogen carbonate would have been the acid present in this drink. Plan and investigation. You must always know that in planning, what is your objective? The objective here is which one has the highest concentration of phosphoric acid. So this is the objective here. To find out concentrations, there are a couple of things that we can do, but then you must always remember that in any experiment, what are you trying to find? This is what you want to find, okay? And then how are you going to find it? Identify how your results will tell you. So this is the analysis as well as the methodology, okay? Now to find that, we need to change something. So we are changing just the different drink. We are changing the types of drinks, the 2 different brand of drinks there. And having done that, we need to compare something. So we need to keep constant. Something to keep constant is what you call control variable. So control variables are very, very important in every single experiment. So in these control variables, what are we going to do? Well, it depends on what kind of experiment we're talking about. Well, we can think about titration. Titration is probably one way to go. So the titration would be, you will need to find out how much acid is in here. So you need what was I going to say? You need to titrate against a non-concentration of a base, because this is the acid. So what we can do is we can do titration we can perform acid-base titration, for example. We want to find out the acid. Okay? So to find concentration of the phosphoric acid. This is concentration of the phosphoric acid. So we will have a fixed volume. So use a fixed volume. Example, pipette out maybe 25.0 cm cube of each drink into separate conical flask. So you're gonna do different experiment, right? So you pipette out something into a conical flask. But what do we need? Okay, we need to titrate against an alkali. So acid plus alkali, acid plus base. So example, NaOH aqueous of non-concentration. You must know this concentration, otherwise you don't know the mole that you're going to use. So i.e., I don't know, you just give example 2 mole per dn³ or 1 mole per dn³ concentration. Fill a burette with this. Fill a burette with this NaOH. So what we're going to do, 1, 2, 3. What can we do in our experiment? So for each drink, perform titration with indicator so that you can see color changes with indicator to see color change at the end point. End point meaning at neutralization point, when things get neutralized exactly. This is the end point. But when you do titrations, you don't just do once. So what we must say is we gotta repeat titration result. So we are not trying to make crystal or anything. We just need to repeat titrations until results are consistent. That means your volume of your titer are consistent, and we gotta say the usual thing within plus minus 0.2 cm³. This is acceptable for IGCSE as well as all level standards. And then we will know that they will give you average titer. So average the best titers. That means the accurate titers that are within plus minus 0.2 cm³. And repeat the procedure. Repeat procedures for the other drink after you have finished the titration for one particular drink. Now we're going to talk about the analysis of result. So for each drink, we had same volume pipette out. In each titration. Correct? So that means you have, I don't know, 25.0 cm³, what is this, value coke and cola. 25 cm³ of value coke versus 25.0 cm³ of Coca-Cola. Was it? Coca-Cola. That is Cola. It's a bit of a funny name, Cola and Cola. So that means whichever one that requires more NaOH will be having higher concentration. So whichever titer, that means the volume of NaOH aqueous is higher, means that the drink is more concentrated, or it has a higher concentration of the phosphoric acid, because we have used the same volume of the acid, and we will have same concentration of the NaOH in the burette, and whichever one that you need more NaOH to react with, that will be the one that is more acidic, so a higher concentration of the phosphoric acid. I wonder how many marks this one is. There were around 6 marks. I think I've just kind of analyzed all the information there already. So I've got 7 points, but probably you get away with the idea of what are you going to do, how you're going to do it with all the correct apparatus. And you're going to repeat titration until your results are consistent within this acceptable margin there. average of titers, but you must talk about comparisons because it says describe how in your answer, how your result will tell you which one contain more or higher concentration of the phosphoric acid. So, I mean, that's pretty much all the space I have there. But what else could I have talked about here? This reaction or this question is about, reaction between a carbonate or a hydrogen carbonate and also acid. We are producing a gas. So whichever one that contain more acid, but don't contain this strong acid, whichever one that contain higher concentration of acid should react to give you more carbon dioxide. So this is an alternative answer, alternative method. We could do rate of reaction method. So we could do perform rate of reaction experiment. So in terms of rate of reaction experiment, it means that, measure the volume of gas. So there are two ways here. You can measure the volume of gas in a fixed time, volume of gas produced in a fixed time. So that means like after 10 seconds or 20 seconds, measure the volume of gas in a gas syringe. So using a gas syringe, you can measure the volume of gas. Okay, but then we have to keep the volume of drink constant. What else? Temperature constant, because temperature could affect rate of reaction, so temperature must be constant. So these are what you call your control variables, because you don't want it to change in your experiment. They could affect rate of reaction. We measure the volume of gas. So use stopwatch to monitor time. For example, after 2 minutes, let's say after 2 minutes or after 1 minute, how much gas was collected. So the reaction might still be going on, but how much gas was collected after 2 minutes for each. And then repeat the same thing, repeat for the other drink, collect the volume of gas as well, collect volume of gas. And then we compare, because the last bit is about comparison. Compare the volume of gas collected in the fixed time. So collected in, let's say, 2 minutes, as I mentioned earlier, can be 2 or 3 minutes, up to you, but it has to be fixed time for both drinks. And then the greater volume of CO2 gas collected, therefore the more concentrated is the acid, because we have reacted it with the sodium hydrogen carbonate, right? So the more concentrated the phosphoric acid is in the drink. I think I've forgotten something, because we are reacting this with sodium hydrogen carbonate. So we're reacting this with sodium hydrogen carbonate. I have made a mistake, and the reason was because I have done the titration with NaOH. I should have done this titration with NaHCO3 aqueous. I should have done this with NaHCO3 aqueous. And then I should have done this with whichever the volume of NaHCO3. So all sodium salt will be soluble, including sodium hydrogen carbonate. So instead of using NaOH, I should titrate with NaHCO3. Well, the titration method was one thing, but the other one, sodium hydrogen carbonate, could also be used for this reaction here. So we are using a solution of it, or we could use a solid of it. Gotta keep the same amount. So I must say same amount. So can I say use the same amount, keep the amount or volume. I don't know whether we use solid or solution, but this will be the amount of the sodium hydrogen carbonate constant, so that if you use more of these, of course you might get more carbon dioxide. So we want to keep it constant for all our experiments. I talk about gas syringe here, volume of gas collected inside a gas syringe. How much gas was collected in a gas syringe? I must really mention the apparatus so that I'm as complete as possible. Was collected in a gas syringe, as that is what you use to collect the volume of gas there. And I think that is pretty much it for this alternative method. Not only that, there was measure the volume of gas produced in a fixed time. As for this kind of rate of reaction experiment, what I can do is I can talk about measuring the time, because there is a rate of reaction. So another alternative method, there's always more than one method to do planning, especially when you're thinking about rate of reaction. Rate is to do with change in amount over time. So the previous part of the question, I talk about, in a fixed time. So if I talk about fixed time, then the amount, which was the volume of gas collected, was changing, and that would tell me the rate of reaction there. But here, if I do rate of reaction experiment, I can measure the time taken. So rather than measure the volume of gas produced in a fixed time, I can measure the time taken to collect a fixed volume. So there are always two ways. Previously, in the first part, I talked about the change in time being constant. In a fixed time, how much gas was produced. Here, I'm going to say how much time is going to take to produce a fixed amount, to collect a fixed volume of gas. The idea is pretty much the same. You're going to keep the same amount of sodium hydrogen carbonate used, keep the volume of the drinks used the same, the Coca-Cola and the value Coke, keep temperature constant. Here what we're going to do is we're going to use a stopwatch, of course, to monitor the time taken, because there's the apparatus you use. How much time will be taken to produce a fixed volume of gas. So you gotta give a quantity. So example, I don't know, 10 cm cube. If you can say 20 cm cube. 1000 cm cube is probably too much to bother about doing experiment in the lab for gas. So to produce a fixed volume collected inside this apparatus called a gas syringe. Now the last bit is about comparison of result, right? So whichever reaction was faster, i.e. shorter time to collect a fixed volume of gas, will have higher concentration of the phosphoric acid, because we know concentration is in mole per dm cube. The higher your concentration of acid, the higher the amount of H plus per unit volume. So there is more H plus per unit volume. And if you have more H plus per unit volume, therefore they can collide more frequently. They will come into contact with each other more frequently with the hydrogen carbonate. Therefore, faster rate of reaction. So that one will come from the more concentrated solution of the phosphoric acid inside one of the two drinks. This is about analysis of the result to basically, tell you exactly what you're looking for, which is which drink contains higher concentration of phosphoric acid. We can do rate of reaction experiment. We can do a quantitative experiment with acid-base titration as well. So pardon the fact that I used sodium hydroxide earlier, should have been sodium hydrogen carbonate there. So I've changed that as well. And I've changed the last bit by comparing the average titer against the how much average titer of the sodium hydrogen carbonate solution, because when we do titration is for solution, and we know that sodium hydrogen carbonate is definitely soluble because all the Na plus salts, including the hydrogen carbonate or the carbonates, are going to be soluble, part of solubility rule there. And I think that's it really for this 6 marker question number 4 here. So there are quite a lot of points that you can have. There are more than one way to do this particular question. So yeah, I hope your way will have score at least as many of the points as possible. So thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. And do share the channel with others if you have found the content useful. Thank you for watching. I'll see you in the next tutorial video.